Okay, this is the start of chapter 2, and in 2.1 we're going to look at power, polynomial, and rational functions. So we're going to look at these types of functions specifically, one at a time, talking about all of their characteristics. So the first one is power functions. Several of our parent functions that we looked at in chapter 1 could be classified as power functions. So a power function, they are types of monomial functions. And if you remember, monomial means they just have one term. There's no addition or subtraction. And monomial functions can be written a couple of ways. The ones we're going to look at will be represented more like this: y equaling a times x to the n power. Or a more simple monomial function would just be y equals a, where a and n are non-zero constant real numbers. So just to maybe break that down and make it a little more clear for you, if we break down monomial functions, we have just y equals a as a monomial function, and then we have y equals a times x to the n, which more specifically will be the power functions that we're going to discuss as we start. Okay, so the monomial functions that we're going to start first of all, we're going to take a look at these two graphs. We're going to graph and analyze each function by making a table of values. So the first one we're going to look at, letter A, is 1/2. Let's see if I can get that isolated a little better. Okay, that's maybe just going to have to work. Okay. Graph and analyze each function by making a table of values. So we have 1/2 x to the 4th, and we're going to take and plug in some x values and get some y values to take a look at this graph. So let's start with maybe -2. When I plug in -2, I get -2 to the 4th power is going to give me a 16, and then half of that will give me 8. I'm going to plug in -1. -1 to the 4th power is +1, and half of that will be 1/2. I'm going to plug in 0, which of course will be 0. Then I'm going to plug in 1 and 2, which raising those each to the 4th power is not going to have any effect on the sign. So I'm going to again get 1/2 and 8. So as I plot those, I'm going to zoom in on this because these tend to flatten out a little bit at the bottom. I have 0, 0. I have -2, 8. So 2 to the left, and then 1, 2, 3, 4, 5. Gosh, that's going to be way up here maybe. -1 and 1/2. So that's right there. I have 1 1/2, and I have 2 8. So this, very similar to a parabola, but the bottom where the vertex lies is much flatter than maybe a normal 1/2 x squared would be. Okay, so looking at this graph, let's look at some of the characteristics. The domain, as you can see, there's any number that we want we can plug in for x. So the domain would be -infinity to infinity. The range, the very lowest y value that I'm going to have would be 0 because I'm not going to get anything negative, but I am certainly allowed to plug in 0. So my range will be with a bracket 0 to infinity. I have an x-intercept at the origin and a y-intercept at the origin, 0, 0 for both of those. EB stands for end behavior. So as I look at x going to, I'm going to put these both together. As it goes to positive and negative infinity, my function does the same thing. It also goes off to infinity. Is it continuous? Yes, I can draw this without picking up my pencil. Is it increasing or decreasing, and where? Well, we have a critical point at 0, 0. So from -infinity to 0, this is decreasing as we read the graph from left to right. And then after we have that critical point at 0, after that it is increasing. So 0 to infinity is increasing. Okay, so just some characteristics. Doing that should be pretty familiar based on the previous chapter where we looked at lots of these characteristics for studying these graphs. And again, this is the first section for this chapter, so we just want to lay the foundation for the functions that we're going to study as we go through this chapter. Okay, letter B, let's take a look at this one. Negative x to the fifth. So what you need to realize with this one is that it is not raising a negative x to the fifth power. You are taking, make sure you look at this as it is a -1 times x to the fifth. So we just want to be very careful that if you are using your calculator to plug in values, this is the opposite of x to the fifth. So you're not raising it to the fifth power. If it's I mean, you know what I mean. Okay. So let's look at a table of values. Okay, I'm going to plug in 0 to start with. That'd be nice and easy. Of course, I get 0. If I plug in -1, -1 to the fifth power would be -1. But the opposite of that is a +1. If I raise 1 to the fifth power, that's a +1. But then I take the opposite of that, and that's going to be -1. I'll do a couple more, even though I'm not going to be able to fit them on my graph. I can plug in 2 for x. 2 to the fifth power is 32, and the opposite of that is -32. And then if I plug in -2, -2 to the fifth power is a -32, and the opposite of that is 32. So let's see what this graph looks like. I have 0, 0, I have -1, 1, I have 1, -1, and then I have 2, -32. Oh my goodness, that's way, way, way down here. And -2, 32, it's way up here, so it rises and falls very quickly. Okay, so there is -x to the fifth. So our domain, of course, there's nothing I can't plug in, -infinity to infinity. My range, also everything. It spans the entire y-axis, -infinity to infinity. My x-intercept and y-intercept, again, the origin, 0, 0. And behavior. So I'm going to do these separately because they do go to different places. So as x goes to infinity, my function f of x goes to -infinity. And as x goes to -infinity, my function goes to +infinity. Is it continuous? Yes, absolutely. Increasing or decreasing? This is actually decreasing everywhere from -infinity to infinity. Remember, we talked about inflection points and critical points right there at the origin. It has a point of inflection where it does change concavity, but it is still continuing to decrease through that interval. Okay, now those were a couple of specific graphs, but now we're going to summarize this, and this may look very familiar to something you did in Algebra 2. And we also talked about this a little bit in the first chapter. So we're going to sketch a graph of the monomial function f of x equals ax to the n with the following characteristics. So we're going to break this down when n is either even or odd and a is either positive or negative. And you may remember this as the leading term test. So if that rings a bell, this is going to be very familiar. So if n is even and a is positive, well, let's sketch a graph of that. So if it's an even function, maybe it's x squared, maybe it's x to the fourth, and a is positive, so a positive x squared or a positive x to the fourth. We're going to have a graph that will look something like this. So as we look at this graph, it's even, the exponent is even, a is positive. As we look, the limit as x goes to infinity, my function, we'll just call it f of x, also goes to infinity. And the limit as x goes to negative infinity, f of x is still going to infinity. So one thing to notice here is this has symmetry in the y-axis. And so what that means, remember when we did algebraic proofs, for every xy, my function would also have a negative xy. Okay? So now we're talking about the same things that you did in Algebra 2, but now we're talking about limits. When we talk about their end behavior, we're bringing in that word limit. Okay, the next one we're going to look at, if n is even but a is negative. So maybe we have a negative x squared or a negative x to the fourth. So my function is going to do something like this. Okay, so with these, as x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to negative infinity as well. So again, this should be familiar. When you have even functions, as the function approaches positive and negative infinity, your functions are doing the same thing. They're both going off to positive infinity or both going off to negative infinity. Okay, now we're going to look at if n is odd. Maybe we have x to the third, maybe an x to the fifth, and maybe a is positive. Maybe we have 3x to the third and maybe 2x to the fifth. Those graphs would look something like this. Okay. All right, so that's an example of an odd function where it may be where a is positive, so the leading coefficient would be positive. With this, as x goes to infinity, f of x also goes to infinity. As x goes to negative infinity, f of x also goes to negative infinity. So again, this is a situation where you have your odd function, where the leading exponent is odd, and they are doing opposite things as their end behaviors. Okay, they don't go to the same place, they're doing the opposite. This right here, these type of functions often have symmetry, as you are already familiar, in the origin. And if they have symmetry in the origin, they are odd. And one way, remember, that we can tell is if I have an xy in the function, I'm also going to have a negative x, negative y. Okay. And then we're going to look at if n is odd and a is negative. Maybe I have a negative 4x to the third and a negative 7x to the fifth. That function is going to look something like this. As far as their behaviors. So, as x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. So again, odd functions doing opposite things, and one of the keys from your leading term test was as x goes to infinity, if the leading coefficient was negative, your function would go to negative infinity. So that should be pretty familiar to you guys. Okay, now we're going to go to reciprocal functions. Okay, so reciprocal functions, again, we've studied these in Chapter 1. We're going to do them again here, and as we go throughout the chapter, we'll do a bit more work with them as well. So reciprocal functions have the form f of x equaling a over x. And they are graphed. Actually, let me draw attention to that. So here's my function. They're graphed when the power function has negative exponents. So the power function that we just talked about, this may be a x to the negative n. So now we could say, with a power function, n would be positive, but now I would say a over x to the n. Now I have what's referred to as a reciprocal function, and it's also a type of rational function as well. Remember, when the variable appears in the denominator, this is important, the graphs are going to have undefined values of x and discontinuities. Remember, they're going to have vertical asymptotes. Let me get myself a little more room on that. So, vertical asymptotes or points of discontinuity. Okay. All right, so let's look at a couple of these examples. Graph and analyze each function. So I have 3x to the negative 2. So if we write this using the exponent rules that we know with negative exponents, our f of x can be rewritten as 3 over x squared. Now when we studied our parent functions, off to the side here, 1 over x squared, if you remember, looked something like this. Okay. So let's make a table of values over here to the side and just plug in a few so we know what the shape of that should be. This would be this parent function here, 1 over x squared, that we looked at in chapter 1, but now we have a 3 out there, so it's going to rise maybe a little steeper, coming in towards 0 from both sides. So the points that I've picked, when I plug in 0, of course, that's undefined. We have a vertical asymptote there. I picked 1, and that gives me 3 as a y value. I picked 2, and that gives me 3/4 as a y value. And I also picked -1, which also gave me 3. These are going to be symmetric over the y-axis, if you remember that parent function, because again, all we're doing, we're not shifting left to right, we're just stretching it, a vertical stretch or expansion by a factor of 3. So as I draw this vertical asymptote, making sure we see that, and then I have the point 1, 3. I have the point 2, 3/4, and I know that the parent function of this graph looks like this. It is also bottom heavy. From our horizontal asymptotes, we know that that's a case 1 that you've talked about in the past, so that automatically has a horizontal asymptote at y equals 0. Oh, and I also had the point 1 negative, or -1, 3. Let me finish graphing this. Okay, my drawings definitely don't always look symmetrical. Actually, let me clean this up because we also know we would have -2, 3/4. I can do a better job of that. All right, very good. Okay, let's look at a few more characteristics of this. So the domain, we just are not allowed to have x. So from -infinity to 0, and then from 0 to infinity, we're allowed to have anything we want but 0. My range, if you look at the range, there's nothing in that will be negative. Everything that you plug in for x, you're going to square it, so you won't get any negative values. So even though we can't equal 0, it starts from 0 to infinity, not including infinity for our range. X-intercept and y-intercept, it doesn't have either of those. Those are both undefined, won't exist. And let's look at end behavior. As x goes to infinity, f of x is actually going to 0. And also, as x goes to -infinity, f of x is approaching that horizontal asymptote again, which is 0. Is it continuous? No. This has infinite discontinuity. And increments of increasing and decreasing. As you read this graph from left to right, it's increasing from -infinity all the way up to 0, and it's decreasing from 0 to infinity. Okay, so there's our first look at our first reciprocal function. Okay, let's look at b. F of x equals 2x to the -3rd power. So if we rewrite this, change colors here, I'm going to rewrite this as f of x equals 2 over x to the 3rd. Okay, and I just want you to notice the difference here in the exponents. Our first one had an even exponent, and now we're looking at an odd exponent. in the denominator. So we want to be conscious of how this does change and affect the graph. So essentially, we have 1 over x cubed, and I'm not sure if you remember the parent function that we looked at before, which again, x is out here, 1 over x. These always looked something like this from chapter 1. That may be familiar to you. So keeping that in mind, let's find some values that we could plug in. 2 over x cubed. So I did put 0 in there, but it is going to be undefined. There's a vertical asymptote again at 0. And this is bottom heavy once again, so it will have a horizontal asymptote at y equals 0 as well. Okay, then I plugged in -1, and just for the sake of time, when I plugged that in, I got -2. When I plugged in 1, I got +2. I used 2 for x, and I got 1/4. And I plugged in -2 for x, and I got -1/4. So as we plot those points, -1, -2 would be down here, +1, +2 up here. So again, we can see they're in opposite quadrants, diagonally opposite from each other. 2 and then 1/4, and -2, -1/4. So we have relatively that same shape as that parent function from chapter 1. But this would have a vertical expansion by a factor of 2, and of course it is x cubed instead of x. So let's look at these characteristics. So the domain for this, once again, -infinity to 0, not allowed to have 0 in the denominator, and then 0 to infinity. The range is actually going to be -infinity to 0 as well, and 0 to infinity. Just can't have that horizontal asymptote value of 0. X-intercept, there isn't one, does not touch the x-axis, and y-intercept, there's not one of those either. End behavior. So as x goes to infinity, f of x once again approaches the horizontal asymptote of 0, and as x goes to -infinity, f of x still approaches the horizontal asymptote of 0. This is not continuous. It has infinite discontinuity once again. And increasing, decreasing, actually this entire, wherever the graph exists, as you move left to right, these tend to be a little confusing. It is always decreasing as we move left to right from -infinity up to 0. I have to stop there because we hit an asymptote. So I'm decreasing as I ride that graph to 0. And then when I get on the graph on the other side of the y-axis, I'm decreasing once again from 0 to infinity. Okay. So now we're going to take those two examples and we're going to characterize the graphs of these reciprocal functions like we did on the first page with our power functions. So we're going to sketch a graph of reciprocal functions with the following characteristics. So we have a times x to the -n, and once again, just as a reminder, that's just like a over x to the n. Now, if you have Desmos and you're familiar with Desmos, that's another great way to practice graphing these. Okay, so the first one, if n is even and a is positive, so maybe we have 2x to the -2, or we have 5x to the -4. Again, that's like 2 over x squared and 5 over x to the 4th. So something like that, that kind of scenario. These graphs will look like this. Kind of reminds me of the old Atari symbol. Dating myself. Okay. So this, again, if you follow that leading term test, well, with this one you really can't. I'm sorry, I take that back, because we have it approaching 0 as our end behaviors go to positive and negative infinity. Okay, as you can see, this one right here, this has symmetry in the y-axis again. And so that would be typical of n being even and a being positive. And again, this would be an even function, not just because it's x to the x squared, but because it has symmetry in the y-axis. If n is even and a is negative, maybe I have a negative 3 x to the negative fourth, or maybe a negative x to the negative 2. Again, that would be negative 3 over x to the fourth and a negative 1 over x squared. So those graphs would look more like this. Making the whole function negative is going to reflect that in the x-axis. So it would flip that graph upside down. Okay, then let's characterize n being odd. So if n is odd, let's say maybe we have, and a is positive, so let's go with just x to the negative third, and maybe we'll go with 5x to the negative fifth. So n is odd and a is positive, so that would be like 1 over x cubed, or 5 over x to the fifth. So if I take a look at those graphs, we remember when it's odd, kind of similar with the leading term test, they do opposite things. Those graphs are going to be in the first and third quadrants. And then vice versa, if we have n being odd and a being negative. So maybe I have negative x to the negative third and a negative 5x to the negative fifth. This would be characteristic of them. I'm going to have these with values in the second and fourth quadrants. And so in the bottom, when n is odd, these have symmetry in the origin. Okay, so that takes us through reciprocal functions. On the next page, we have rational functions. Now, rational functions are going to kind of take us through this first page, and then well, okay, no, we're good. Okay, so rational functions, we really did discuss just previously some rational functions. 1 over x cubed, anytime you have a function where you have a fraction, the denominator cannot be 0, you have a rational function. But more specifically, we're going to look at rational functions that have rational exponents. So remember that x raised to the p over n power, we've kind of broken this down previously. This means the nth root of x to the p power. If n is an even integer, then the domain can only include non-negative values, and I would say positive, but 0 is also included. So again, if you're taking an even root, a square root, a fourth root, a sixth root, you can only have non-negative values. And one of those reasons is that we can write that as a radical function, which we'll get to in just a little bit here. Okay, so let's take a look at some rational functions that have rational exponents. So graph and analyze this function, x to the 5/2 power. Now, I'm going to cheat just a little bit because radicals are still coming, but remember, this is my root, the denominator is my root, and the top is my power. So I can also write this as the square root of x to the 5th, or, if you remember, the square root of x to the 5th, where I can put that on the outside. Now, because this is a square root, I can only put in domain values that are non-negative. So let's do a table of values. And I am going to start with 0. So if I plug in 0, I raise it to the 5th power, that's still 0, and the square root is 0. Then I'm going to plug in a 1. As I take the square root of 1, I get 1, and raise that to the 5th power, it's still 1. I'm going to plug in my next perfect square because I'm thinking about putting it right in there, and I'm going to put in 4. If I take the square root of 4, that gives me 2, and 2 to the 5th is 32. Gosh, that's going to be way off my graph. That's really steep. So let's graph this. I have 0, 0, 1, 1, and then off the charts I have 2, 30, or I'm sorry, 1, 1, and then I have 4, 32. 1, 2, 3, 4. I mean, goodness, it's like way, way, way up here. So this is just going to extend. Okay, so let's talk about the characteristics for this. The domain is going to include 0 and goes off to infinity. You can plug in any positive x value after that that you want. The range, same thing, from 0 to infinity. The x-intercept is 0, 0. The y-intercept, also 0, 0. End behavior. We only need to look at x going to infinity, and when we do that, f of x also goes to infinity. Is it continuous? Yes. When we start drawing it, we don't need to pick up our pencil, and it is increasing only from 0 to infinity. Okay, so let's look at example B. We have 6x to the negative 2/3 power. Let's see. Okay, so now as I look at this, keeping in mind what the negative does, that's going to take it to the bottom, 6 over x to the positive 2/3 power. And I am going to rewrite this with a radical, 6 over the cubed root of x squared, or I can write it, whichever is more convenient as you're plugging in your values, 6 over the cubed root of x, and then I can square that afterwards. So after rewriting this function, now I'm going to plug in some x and y values. Now, if I go to plug in 0, I'm not allowed to do that in this case because it's in the denominator, so this is going to be undefined. There's actually a horizontal asymptote at 0. It would be considered bottom heavy. So then I'm going to plug in 1. As I plug in 1, I essentially get 6 over 1, which is 6. I can plug in negatives now because I'm taking an odd root. So the cubed root of negative 1 is negative 1, but I square it, so I get positive 1, and then 6 over positive 1 is still 6. So be careful with that. Take your time as you plug in values. If you don't have your calculator, be very careful when you plug in values and raise them to powers. I'm going to plug in a perfect cube now since I'm taking the cube root. I'm going to plug in 8 and then negative 8. As I take the cube root of 8, I get 2. Square that is 4. And then 6/4 is 3/2 or 1.5. When I plug in negative 8, I get negative 2. And when I take the cube root and then I square that, I get 4 again. And so 6 over 4 is still 3/2. So we're going to plot these points. Oh, sorry, I forgot the vertical asymptote. 0 is undefined. Oh, okay, so 0 being undefined in the denominator, vertical asymptote, and then bottom heavy gives me the horizontal asymptote. Okay, I don't know if I misspoke earlier. So 1, 6, 1, 2, 3, 4, 5, 6, negative 1, 6, so we see some symmetry. 8 3/2, which is 1.5 right here, and then of course negative 8 3/2 again. So I have a function that looks like this. Okay, so let's talk about the characteristics. The domain, you can plug in anything you want but 0, negative infinity to 0, and then 0 to infinity. The range is from 0 to infinity. X-intercept, there is not one, and there is no y-intercept either. End behavior. As x goes to, and I'm going to do this all in one, positive and negative infinity, f of x goes to 0. It does the same thing as you approach positive infinity or negative infinity. Continuity, no, it's infinitely discontinuous, or it has infinite discontinuity. Increasing or decreasing, well, it does do some different things. As you read it left to right, it is increasing from negative infinity to 0, and then it is decreasing from 0 to infinity. Okay. So, the next thing we're going to jump to in the notes is a power regression. And I apologize, I don't have a virtual TI-84 that I can show you. So I'm going to walk you through these steps and try to make some notes off to the side as to how to put these in here. Okay, so as we do a power regression, and this will be with the calculator, this is like a power of a power function or a power of best fit. This regression line, but the values are going to generate really a power function. So for example 4, let's read this data. It says it represents the body length in L in centimeters and the mass M in kilograms of several African golden cats being studied by a scientist. So the length is going to be our independent variable. And when you plug this into the calculator, guys, this is going to be your L1. Then your mass is your dependent. Your mass is going to depend on your length. So this would be your dependent variable. And this will go in to L2. Okay, so we see we have lengths, and the mass, again, is in kilograms. Make a note of that. And this is in centimeters. Okay, so create a scatter plot of the data using your calculator. Okay, so I have mine in my hand. I'm going to kind of walk you through this. You might want to pause the video while you go ahead and put some of these values in. You're going to go to Stat first as you plug this in. You're going to go to Stat, then you're going to already be on Edit, and you're going to hit Enter. And now you plug in values. For L1 and L2. Okay, once you have those values plugged in, if you want to see the scatter plot, then we're going to have to take some different steps. You're going to go to second y equals to turn your stat plot on. And it'll be that first one. So this is where you want stat plot on. Making sure that the type, as you look at the graph, is the scatter plot. Your X list is L1, your Y list is L2, and then you can of course choose the marker. And so once you have those data values in, you can just hit zoom 9 and it will show you that scatter plot of values, and it will fit those perfectly into place. Okay? So, and I apologize, I did not plug all those values in, so I'm not really looking at it. I'm just trying to walk you through the steps. So zoom 9 gives you a look at that, that array of data values. They're not going to be in a perfect fit. It's not going to be perfectly in alignment, but it's just, again, a scatter plot. So now that we have the scatter plot, we want to generate an equation. So we're going to go back to, now in B, determine a power function. And they tell us right there, power function. So we're actually going to choose that from the menu when we get there. So you want to go back to Stat now. And we don't want to edit anymore. We want to go over to Calculate. And because it says power function, you're going to go all the way down. And mine is the capital letter A. It's past the 0. And you're going to choose power reg for power regression. And when you do that, it asks you, do you want X list to be from L1 and your Y list to be from L2? Yes, yes, yes. Then you're going to go down to calculate. And once you do that, it will give you your values. Now, you have one of two choices right here. You can either copy those values down, and then you can recopy them into Y1, or I'm going to give you a few quick steps so that you can paste it right into Y1 and graph it from there. So you're going to go to Y1 and clear it. Make sure there are no other variables or equations in there. Go to Y1, clear it. Then you're going to type, or you're going to hit vars, which is to the left of the clear button. We are working with statistics. So then you'll hit statistics or choose statistics, then equation, and then regression equation, REGEQ. And at that time, it should paste that equation in there, and then you can hit graph, and you should see that graph cut through those points with that new equation that you've generated from there. Okay, so the equation that I got, that my calculator gave to me, is m equals 0.02 x to the 1.54. I rounded to the nearest hundredths place, sorry. Rounded to the nearest hundredths place, and there's my equation. Now that I have that into y equals, I can use that to make predictions. For example, in number C, or letter C, use the data to predict the mass of an African golden cat with a length of 77 centimeters. So you could always plug 77 centimeters in for X. You can go to your table and go to 77 there, or you can go to value and have it calculate the value with 77. That shouldn't be a problem. Let me know if you can't get that and I can help you. But using my equation, the mass I got was 14.08 kilograms. Okay, and yours should be very, very close to that. Okay. All right, the last type of function we're going to talk about are radical functions. And really, just a minute ago, we looked at making those rational exponents radicals. So we've already really discussed this quite a bit. So as this says in the gray box, we briefly reviewed rational exponents a moment ago. Let's look at them in more depth in terms of radical functions. So radical functions can be written in either exponential form, for example, what we just saw, f of x equaling ax to the p over n, or radical form. And if we wrote that same function in radical form, it would be f of x equals a times the nth root of x to the p power. And remember, the p can go on the outside or underneath the radical. In these forms, it's important to remember n and p are positive integers greater than 1 and no common factors, which just means they're already simplified. And there's no need to mess with it. So let's look at these two examples. Graph and analyze each function. Example A, f of x equals 5 times the square root of 2x to the third. So with this one, square root function, we have again a positive root. Oops. So I'm going to plug in some values. I can absolutely plug in 0, and I will get 0. So this is a square root. I can plug in 1, but that's not going to give me a perfect square. I'm going to actually plug in 2. Now 2 cubed is 8. 8 times 2 is 16. The square root of that is 4. And 5 times 4 is 20. So this increases so fast. I go from 0, 0 to 220 way up here in the rafters. So, oh my goodness, just shoots way up there. All right, so let's look at the characteristics. The domain is including 0 from 0 to infinity. Range is also from 0 to infinity. The x-intercept is 0, 0. The y-intercept is 0, 0. End behavior, we're just going to look at x going to infinity. F of x also goes to infinity. It is continuous, and it is increasing. It is increasing from 0 to infinity. Okay, let's look at the next one. I have f of x equaling 1/2 of the 5th root of 3x minus 4. Okay, so if you can remember the cube root of x function, this was like a cubic, but it was laying on its side. So 1/2 is like a vertical compression, so it's even going to make that more narrow. 5th root is going to make that even more narrow versus a cubic root. So this one, you might want to just put this in your calculator. We're only going to, I just have one point that I put in here, and then from there, just knowing kind of the pattern, you can get some points from your calculator. I put in 1 because I would get 3 minus 4 is a negative 1. The 5th root of that is negative 1. Times 1/2 is negative 1/2. So I have 1, goodness, and negative 1/2 right there. So this graph is so narrow. Oh, it's probably not even a great start here. So narrow. Just kind of staying along like that. Okay. And again, you're taking an odd root, so you can plug in negatives and positives, anything you want. Okay, so domain is going to be all real numbers, negative infinity to positive infinity. Believe it or not, the same thing for range, even though it doesn't look like it's going to span the entire thing. Eventually it would. The x-intercept, so this is where you'd probably want to go to your calculator for something like this and just calculate that value. Remember, the x-intercept is where you'd set the function equal to 0, so y equaling 0. Y-intercept, let x equal to 0. So I actually have already calculated these. The x-intercept is 1.330, and the y-intercept is 0 and negative 0.6598. Goodness. Okay. So you may want to pause and make sure that you are okay finding those intercepts on your calculator. That's not something we would ask you to do by hand. So just make sure that you can handle the technology to do that. Okay? End behavior. So as x goes to infinity, my function, believe it or not, will go to infinity. And as x goes to negative infinity, my function will also go to negative infinity. Yes, it is continuous, and it is always increasing from negative infinity to infinity. Okay, so the last thing we're going to do is characterize these radical functions. So we're going to sketch a graph of the rational function or the radical function, the nth root of x, with the following characteristics. So if n is even, this could be square root, this could be 4th root, this could be 6th root. When you have this happen, you are only going to have your positive integers, something like this, or again in example A it was curved more like that, but basically it's just going to exist in that first quadrant. When n is odd, so maybe we have the cubed root or the 5th root or the 7th root, those can be anything for the domain, negatives and positives, and those will be laying more flat on their sides. Okay, so that takes us up through characterizing some different functions that we're going to be studying. The last page, we're going to jump to something different, solving radical equations. So kind of an interesting little section to put at the end of this, but here we are. So solving radical equations. A radical equation now is any equation which a variable is in the radicand. So in other words, underneath the radical. So you have some kind of a variable under here. To solve a radical equation, we've got 3 steps to help you. First of all, you want to isolate the radical if you can, or at least one. So isolate the radical. Then you're going to raise to the appropriate power. So, for example, if you were taking a square root, you'd raise to the 2nd power. If you were taking a cube root, you'd raise to the 3rd power, so that we would undo and get rid of that radical so that we could get to the variables underneath. And now step 3, hopefully we've been able to get rid of those radicals. Sometimes, like you're going to see in some of these problems, we have to do that more than once. So we'll walk through those steps here in a minute, but then you're on your way to solving. And one red flag area, let me get the red out. I'm a terrible drawer. Okay, we need to check for extraneous solutions. That's always fun, I know. But the algebra, in truth, the algebra sometimes gives us solutions algebraically that look like they'll totally work, but because of squaring radicals and some of the techniques that we have, although the algebra may allow it and it looks like a solution, in the original equation, it's not going to work for one reason or another. So just always need to be careful of that. Okay, so let's solve these 3. Now these are 3 these are 3 fun ones. I'm going to tell you right now. These are not your Algebra 2 type radical equations. These are at a pre-cal level, maybe pre-AP Algebra 2, but these are a little more challenging. So starting with example A, or example 6, letter A, we're going to isolate the radicals. So we're going to add 2, simple enough. That cancels. I'm going to get 2x plus 2. And on the right, I still have 100 minus 12x. Okay, now, since it's a square root, the appropriate power is going to be to square both sides. So on the right, I have my 100 minus 12x. And on the left, I'm actually going to need to FOIL that out. So if you need to do this on a separate space, please do that. If you're not good at doing it in your head, please write it out so you don't make any careless mistakes. When I do FOIL this out, I'm going to get 4x squared plus 8x plus 4. So this is a quadratic. I want to get my like terms together. So 4x squared is going to stay. I'm going to add 12x to my 8x and get plus 20x. And I'm going to subtract 100 and get a negative 96 equal to 0. Okay, so now we're just solving a quadratic. I do have a greatest common factor of 4, so I'm going to take that out. I'm left with x squared plus 5x minus 24 equals 0. Now if I divide both sides by 4, that's going to make the 4 go away and it'll still equal 0. Now I can factor this, x squared plus 5x minus 24. 2 factors that multiply to give me negative 24 that add up to give me 5 are going to be positive 8 and negative 3. So I would have x plus 8 and x minus 3. So setting both of these factors equal to 0, I would get x equal to a negative 8 and x equal to 3. Okay, so I just need to double check. The algebra told me that these are my solutions, but if I go back and I plug in negative 8, it actually is not going to work right here. If I plug in negative 8, on the left I would get negative 16. And on the right, let's see, I would have, hold on. So I would have 100 minus 96, which is 4, The square root of 4 is 2, but then I would have 2 minus 2, and that does not equal 16. I would get 0. So 8 does not work. If I plug in 3, I would get 2 times 3 on the left, which would give me 6. And then, let's see, on the other side, I would get the square root of 36 underneath, and which is 6, and then 6, hold on. Okay, 64. Oh, sorry, underneath I would get 64. And so that 100 minus 36 is my 64. Take the square root of that, which is 8, and 8 minus 2 still is 6. So my only solution is x equals 3 for this one. Okay. All right, let's try letter B. Okay, here we go. The first thing we're going to do is isolate the radical. So I'm going to subtract 14. And I get the cubed root of x minus 5, all squared underneath there, is going to equal 36. Okay, so if it's the cubed root, the next thing I'm going to do is I'm going to cube, I'm going to cube both sides so I can get that radical out of there. So x minus 5 squared is going to be 36 cubed. Now, that's 46,656. All right, let's FOIL the other side. X squared minus 10x plus 25 equals 46,656. Okay, and then I'm going to take 25 minus 46,656, and to set that equal to 0, x squared minus 10x minus 46,631 is equal to 0. So this does not look like it would be factorable, so we're going to go ahead and use the quadratic formula. So x equals negative b, so the opposite of negative 10, plus or minus the square root of negative 10 squared minus 4 times 1 times a negative 46,631 all over 2 times 1. So these are some pretty big numbers. And as I did the math on this, not even wanting to mess with the 46,631, it actually does work out pretty nice. So this is 10 plus or minus. Once I do 100 plus, that's going to be 186,524. I'm going to have 186,624. Believe it or not, you guys, that is a perfect square. How nice. Over 2. So it is 10 plus or minus. The square root of that is 432 divided by 2. So when I do the math, 10 plus 432 is 442 divided by 2. That's 221. And 10 minus 432 whoops, sorry. That's going to give me a negative 422 divided by 2, which is a negative 211. And those actually do work. So believe it or not, we do end up with a couple of integers. Whew, that was a big one. Okay, and the last one for the section is the following. So we have one radical isolated, but not the other. So we're going to start out by squaring both sides. It's not going to fix our problem completely, but it's a start. So we're going to square both sides. I'm going to have x minus 2 is equal to, now you are going to have to FOIL this. So FOIL very carefully. My first is going to give me 25. And then my outer and my inner are both going to be negative 5 times the square root of 15 minus x. So when I add them together, I get negative 10 square root of 15 minus x. And then plus that quantity, 15 minus x. So I still do have that radical in there. I have one left. So now I want to isolate that radical. I'm going to combine some like terms and isolate that. So I do have 25 plus 15 on this side. So I do have a 40 minus an x, and then minus 10 times the square root of 15 minus x equals x minus 2. I'm going to subtract 40 and add x to both sides. Okay, so I now have 2x minus 42 is equal to negative 10 times the square root of 15 minus x. So at this point, a lot of people would want to divide by negative 10 because technically we want to isolate that radical. But watch what would happen. If I divided everything by negative 10, I'm going to get some fractions over here, and that's going to really muddy the waters and make things kind of ugly. So I'm going to suggest this. I'm going to suggest that right now, let's do a different color. Right now we square both sides, and this avoids fractions. And if you want, you can factor that 2 out and make that 2 times x minus 21, but you still are squaring that whole side. So just be careful there. On the other side, when I square negative 10, I get 100. And when I square the square root of 15 minus x, I get 15 minus x. And now my radicals are gone. Still kind of messy, but we're going to start to clean this up a little bit. Okay, so on the left, I'm going to square the 2, which is 4, and I'm going to square the x minus 21, and that gives me x squared minus 42x plus 441 equal to 100. Actually, I'm going to distribute that. Equal to 1500 minus 100x. Okay, now I'm actually going to divide both sides by 4. 4 goes into those evenly, so I am left with x squared minus 42x plus 441 is equal to 375 minus 25x. Okay, it's starting to look nicer. Now I'm going to add 25x, getting this quadratic equal to 0, subtract 375. Okay, so I have x squared minus 17x plus 66 equals 0. And believe it or not, this factors. So things that multiply to give me 66 add up to give me negative 17 are going to be negative 6 and negative 11. So x minus 6 equaling 0 is going to give me 6. And x minus 11 equaling 0 is going to give me 11. Now, you really do want to go double check these for extraneous solutions. I already have, and I know that they both work, but you definitely do, especially when you have to square things twice, you definitely want to check those. Okay, this was a long lesson, but there you have it, 2.1.